I can hear you.
Yeah, I would say, yeah, we are thankful to you that last interaction with you was very, very fruitful, and I could learn a lot. My basic issue is that I am unable to see the video on interconnection of the modules in series. I have written to Professor Umanand also a couple of times, 4 days back, and got some reply from Mr. Guru Raj Maya, but I have not been able to view that particular video. That is one. Secondly, the resources in the second week where certain videos are supposed to have been uploaded, those are also not there in the YouTube. So I have lost some interest because when the continuity of the lectures is not there and you don't get the requisite response from the coordinator or from NPTL. I hope I am audible to you.
Yeah, I am hearing you.
Yeah,
Yes,
so I lost that interest, and yeah, so let me see. And I am going through the book where the lectures are written in the text form and try to get a hang of things. So I am slightly lagging behind as far as week 2 is concerned.
So in week 2, you are unable to see this lecture?
Only one lecture, that was interconnection of the modules in series.
This one, na?
And not this one.
Then?
I am talking about interconnections of modules in series.
So these are the...
yeah, interconnections of modules in series. Yeah, this one, interconnections of modules.
This one, interconnecting modules in series.
Interconnection of modules in series. Yeah, I could not view this.
It is, right now it is running.
No, it may be running. And Mr. Maya, Guru Raj Maya, he sent me one video clipping also, but that is only 3 seconds long. And moreover, it does not cover that. So I don't know why NPTEL is unable to resolve such a small issue.
Okay, means you are unable to see this on YouTube.
Yeah, I cannot see that. I am connected on the link which has been sent to me or which is there on the NPTEL. I am unable to access this particular video. So if it could be sent to me, or in case you have access to this, so please, I would request you to share with me on my email ID.
I don't know, but in YouTube it is coming like you directly if you search.
In YouTube it is uploaded?
Yeah, in YouTube it is rerun course, means it has several times it is already run. So you can, it is 7 years ago old course.
Okay, on YouTube it is available because I was trying NPTEL. I was trying the NPTEL web link. So, okay. Yeah. Okay, I'll do that. In case it is available on YouTube, fine. I'll go to YouTube.
Every means all lectures are available on YouTube. You directly search like.
Okay. I am from the phone now today. Okay, fine. Because I called up the customer care NPTEL a number of times, they would just ask, okay, what is your email ID? We'll revert back. But anyway, okay, this is good enough.
Let's see.
Okay, see, fine.
All means it is, see, if this time it is 7 years ago older course, okay, and since it is highly demanded course, that's why it is rerunning again and again. Generally, what happens that after 5 years the course will be closed, but this course is really older and very demanding.
Yeah, thank you so much.
Yeah. Now let me come to this today's class. So a very good evening to everyone. I welcome you all in this live tutorial session number 2, design of photovoltaic systems. So in the last class, we have covered the session number 1, in that we have seen some problems, and there are some problems that I talked that we will see in this session first, and then we will start to solve the problems for assignment 2. So let us have a quick revision about the week 1. So we have seen that these parameters of photovoltaic cell, short circuit current and open circuit voltage, and if we use this mathematical expression from this electrical equivalent circuit, by using the approximation, it is coming approximately equal to photocurrent. And this, we know that photocurrent is directly proportional to solar insolation. That means that the short circuit current varies linearly with the incident solar power. And coming to this open circuit voltage, if we see this mathematical expression of this open circuit voltage, it comes like this. So this in this logarithmical bracket, we can see that this I naught is constant, it is dark saturation current, and this IP is variable photocurrent. And we know that this IP is at proportional solar insolation. That means this open circuit voltage varies logarithmically with the incident solar power. Now coming to this effect of temperature on PV solar cell characteristic. So what are the effect of temperature on the short circuit current, ISC, open circuit voltage, VOC, and maximum power, PM. This short circuit current, ISC, have positive temperature coefficient. That means that if temperature increases, the short circuit current will go up, and vice versa. And this open circuit voltage have negative temperature coefficient. That means it is inversely proportional to temperature. If temperature goes up, then open circuit voltage will go down, and vice versa. And since power is equal to voltage into current, therefore this maximum power is equal to maximum power having negative temperature coefficient, and if its behavior is similar to open circuit voltage. And these are the coefficient for short circuit current, open circuit voltage, and maximum power. With the use of this expression, you can find the short circuit current, open circuit voltage, and maximum power at certain temperature. If these values are specified at some other value, let us say that value is the ambient temperature. So you can find this ISC, VOC, and PM at a certain temperature if this coefficient and other parameters are specified at ambient temperature. So we have seen this in the previous class also. We are just revising and have a quick recap about the previous class. And then we have seen some problems on the efficiency. We know that efficiency of a certain system is that output into the input power. So someone mic is on, please turn it off, because if it is getting recorded and its recording will be not of good quality. Chandni, please turn off your mic. Yes. Chandni, please turn off your mic.
ஸ்டார்ட்அப் ஐடியா வச்சிட்டு அவங்கள இப்ப ரெக்ரூட்மென்ட் நமது ஆல்ரெடி ஆல்மோஸ்ட் முடிஞ்சிருச்சுல. சோ
சாரி
உங்களுக்குள்ள
Are you want to speak something, Chandni? Please unmute yourself if you don't have any query. Now it's okay. Whenever you have certain questions or query, you can ask me. And other time you just keep your mic unmute. Mute your mic. So we are here. So efficiency is output power upon input power, and output power, we can get the maximum output power from the PV cell or PV module is maximum power point voltage into maximum power point current. And input power is depending upon this area of solar cell, and this L is denoting the solar insolation. Since this module includes gaps and cases along with pure cell area, therefore this efficiency of module is always lesser than efficiency of solar cell. And efficiency of solar cell also goes down as T goes up, because we have seen in that since maximum power, peak power having negative temperature coefficient, so if this temperature increases, this maximum power decreases. Therefore, this efficiency of solar cell or efficiency of PV module will go down on increasing the temperature. Now, coming to this fill factor, some of you were asking the significance of fill factor. You can better go to the class lecture, but I have a short summary about this fill factor. So fill factor is a measure of the quality or goodness of the solar cell. It is the ratio of maximum practical power to theoretical idealized power. And a large fill factor is desirable and typically ranges from 0.5 to 0.82. And we cannot get this fill factor equal to 1 because it is impossible to get the operating point for the PV at this VOC and ISC. So this, if you make a straight line corresponding to open circuit voltage, so this is coming like this. So this point, if solar cell is operating at this point, then this is called as theoretical power or theoretical idealized power. So this one is ideal case. And in that case, fill factor comes out to be 1. But this is impossible to get this idealized solar cell. This is the operating, this is the feasible IV characteristic. Here, this one shows VMP, IMP, and this is having, for a good solar cell, it's typically range from 0.7, 0.8 like that. And this blue curve denotes this PV curve. Now here, I want to mention one thing also. If you want to have a good understanding about this various things about the solar PV, then I am recommending one website, that pveducation.org. Here they have good they have good literature about all the solar cell things like properties of introduction, population, light, semiconductor junction, starting from the basic solar cell operation, ideal cells, solar cell structure, light generated current, that is photocurrent, collection probability, quantum efficiency. Some of the things that have not considered in this course, but you can go through for better understanding. And then we have solar cell parameters, IV curve, short circuit current, open circuit voltage. So here we can see this fill factor. And in this website, they have used these graphics for better understandings. Like if you see, if you stretch like this, then this is having cell with higher fill factor. Now, if it goes down like this, cell with lower fill factor. So the lower cell factor will be, the worst fill factor will be like this. If I think here it is not wrong. So if you make this a straight line connecting this ISC and VOC for this IV curve, if your solar cell having parasitic resistance, that means series resistant and shunt resistant. Generally, for a good solar cell, series resistance is lower and shunt resistance is higher. Now, just think opposite. If series resistance is of very higher quantity and shunt resistance is of lower quantity, then you may get this worst quality of IV curve, this joining ISC and VOC. So in this case, suppose this is operating point. So here in this case, fill factor will be this one. So this one is the worst fill factor, and generally this fill factor comes out if you comes out at 0.225 for this triangular curve, and so this fill factor comes when this RS is of very higher value and this R shunt very lower value. We will see this quantity for better understandings on this that website I have just told you. Yes, any doubt? Okay. So we have seen one problems where someone has asked about this battery with a series resistance. So this part has been covered in big 2 lecture. So we have the professor has shown this equivalent how to emulate a PV module with a battery and series resistance. So for this battery with series resistance acting as a PV emulator, what will be the fill factor? So the fill factor always comes out for this case is 0.25, because here if we see this IV characteristics for a battery with series resistance, when it is coming like this one, a straight line. So this is ISC and this one is VOC, and this point is IMP and VMP, and VMP is VOC upon 2 and IMP is ISC upon 2. So if we find this fill factor, either without seeing the data, it always coming as 1 upon 4. So 0.25 is the fill factor for this PV emulator that is having battery with a series resistance. So this is about this fill factor. Anyone have doubt? So coming to this next slide, someone has asked about this impact of series and shunt resistance on the IV curve. Yes. Yes. Anything? You can, if you are unable to, I'm unable to hear you. Vasaveswar Banjiri. You can type your query on the chat box. So, what will the effect of series and shunt resistance on the IV curve, and how it vary this IV characteristics of a certain PV module or PV cell? So, resistive effects for ideal cell, the shunt resistance is infinite and series resistance is of 0. Resistance is of 0 value, 0 ohm. For ideal solar cell, RS is of 0 ohm and this RSH is of infinite ohm. Now for practical cell, this is having certain quantity. So this we call it as parasitic resistances. Both shunt resistant and series resistant are called as parasitic resistance. So what will the impact of this resistance on this IV characteristics we are going to see here. So the resistive effects in solar cell reduce the efficiency of the solar cell by dissipating power in the resistance cell. So this is going to lower down the efficiency of solar cell. We will see that if this radial solar cell, this is the IV curve, and if we are having practical solar cell, then this IV curve will go deviate from this maximum power point that we are having in this ideal solar cell. And the key impact of parasitic resistance is to reduce the fill factor. So the parasitic resistance is reducing the fill factor. And a straightforward method of estimating the series resistance from a solar cell is to find the slope of IV curve at open circuit voltage point. And for parallel resistance, we are going to find the solar slope of IV curve at the short circuit current point. And low shunt resistance causes power loss in solar cells by providing an alternate path for the light generated current, that is also called as photocurrent, IP. Now, for better understanding, you can again refer this material, pveducation.org. Here they have demonstrated in a very good way. Suppose this is the IV curve. Now, let us vary this curve. So here we can see this red one is the ideal cell. Now, if we vary this series resistant and shunt resistant, what will be the effect? And we know that for a good quality of solar cell, this series resistance should be lower. So as we lower down this series resistance, we can see this blue curve, that is this practical solar cell IV curve. This is going towards this ideal curve. That means it increasing the efficiency of solar curve and also increasing the fill factor. So see, if it equates it to 0, then it completely overlap over this ideal solar cell IV characteristics. Now suppose if you increase this series resistance to a very large value, that is undesirable for a solar cell. So it is like a triangular, like a straight line, and it is deviating very much from this ideal solar cell IV characteristics. So this is the effect of series resistance on the solar cell. And if you see this, what does it impacting? This series solar cell, it is impacting the voltage or current. So if you changing this series resistance, it is impacting on the slope of the voltage. This voltage means open circuit voltage, means at this point open circuit voltage. So as we go more, this slope is increasing, and as we go lower, this is coming toward this ideal solar cell, and the slope is going to have infinite value. So as this one, this is the slope is going to have increasing it negative. You can find the slope. I think it will come in negative. Slope will come negative. So this is the effect of series resistance on the IV curve. Now for shunt, let us take this series resistance of solar cell 2.7 ohm per 2.7 ohm per centimeter square. Now for the shunt resistance, the desirable thing for shunt resistance is this: it should have higher quantity. So if you just go to higher, then there is no change, very little negligible change. And if you just go lower value, then it degrades the IV characteristics. So here you can see that this ISC is impacting this current curve, that is 30 at 35 ampere point. So if you are having this shunt resistance of lower quantity, then it means that you are giving path to the current. That means this PV current will go down. PV current will go down, and that also lower down this photo current. Uh, so here we are having this PV current and voltage current. So this PV current also goes down. It deviates from this ISC. So it deviates from the ideal IV characteristic of solar cell. And if you are increasing this shunt resistance, then it overlaps. This current curve overlaps over the ideal solar IV characteristic of solar cell. So I recommend you to go through this PV education.org. Here they have demonstrated almost all the things in a graphical way. So here you can vary all the parameters and see what are the impacts on certain properties or something. Now I think are you able to get this impact of series and shunt resistance on the IV characteristics? So in the last class, we have solved this problem in photovoltaic cell characteristics. The slope of a constant current region and slope of a constant voltage region implies as. For constant current region, the shunt resistor and constant voltage region series resistor will impact the slope of constant voltage region, and the shunt resistant will impact the slope of constant current region. And this one is the ideal cell. This is for ideal cell, where shunt resistance is of infinite value and series resistance is of 0 ohm. And blue one is for cell with R shunt and R series. So here is mistake, cell with R shunt and R series. So here, since this R shunt is of lower quantity, that's why it deviating from the ideal cell. So this one is for practical cell. And this is wide practical cell because it is deviating from the ISC point of ideal cell. So you can say bad practical cell, not good quality practical cell. If it is overlapping at this short circuit current of ideal cell, then you can say this as good practical cell. And this should be little bit till here, this point. Till here, any doubt? Okay. So I strongly recommend, yes.
Sir, this as we know, the losses has been because of resistance. Are these losses due to internal causes of the solar cell, or we are considering circuit also, overall circuit, or just a solar cell?
So means for ideal solar cell, we make electrical circuit like this current source with this diode. And for ideal cell, you have to consider this shunt resistance, series resistance. So whatever the efficiency goes down, you have to
Yes, due to
that
this series and
efficiency goes
parallel
down to
resistance.
yeah.
Okay, sir.
Sir,
Who is
this
asking this? Yeah.
10,
Yeah.
sir. Professor 10.
Who?
This
Okay.
is me, Professor 10, sir.
Yeah. And I also I want to say that some of you may be professor and maybe senior to me. If I speak your name, then please don't feel offended.
Yes, sir.
I means maybe you are a student, you are professor, or you are very senior to me. So please don't feel offended if I take your name.
Okay, sir.
Sir,
Okay.
the series and shunt resistor used, are they used only for modeling or they are present physically?
Okay. They are present physically. Means like how you can simulate the similar type of IV characteristics. Means like you have seen in the sir lecture that they are plotting the IV characteristics of a solar cell. So we know that this characteristics coming from the certain solar cell. But how we can have, how we are getting this IV curve? And sir has described this in, professor has described in the first week one, where how we are getting this IV characteristics of a PV cell from this IV characteristic of a diode, and why this shunt resistant and series resistance comes. So these are, you cannot say these are physical present, means like we have a certain series resistance and shunt resistance present in this PV module. These are virtually present. You can say these are virtually present. Means
Sir,
the
if
impact
this
can be
is only for modeling purpose, then how can we vary this parameter, sir?
modeling purpose. Yes, these are for modeling purpose, and these vary based. We find this series resistant and shunt resistant based on the IV characteristics after finding the IV characteristics of solar cell. So these are fixed quantities for certain solar cell or solar PV module.
Okay, sir. Okay.
No, sorry, for certain solar PV cell, and after doing series and shunt connection, you will get this equivalent open circuit voltage and short circuit current. So these are you can say virtually present. You cannot see a resistant and these are parasitic resistant. You can see in your PV module like we have in the laboratory. Just like other things, like if we are having switches, there we know that parasitic capacitance are present. So you cannot see this capacitance is present there. But the behavior, whatever the behavior, how you can see the same behavior through this electrical model. So for this, we have to connect series resistance and shunt resistance.
Okay, sir.
Okay. And the next question, someone has asked that does the temperature coefficient same in this degree Celsius and degree Kelvin? So can anyone answer this question?
Sir, it doesn't matter much as the change in Celsius is equivalent to the change in Kelvin.
Yeah, they are exactly the same. They are exactly same. Because the conversion for mathematical expression for Kelvin to Celsius or Celsius to Kelvin, it is having addition. So it is varying linearly. They are exactly the same. Because if you see this degree Kelvin is, if you just add to 73.15 into degree Celsius temperature, then you will get in Kelvin. So if the temperature coefficient for P max is given as minus 2.29% per degree Celsius, then you can also write it is minus 2.29 minus 0.29 percentage per Kelvin. And you can also write this for VOC minus 0.23 percentage per degree Celsius. And for short circuit current, you can also write 0.05 percentage per degree Kelvin. Now I am asking you, Miss, it is not. I think it will not covered in the assignment. It will not asked in your exam or assignment. But I have one question that this percentage, like T percentage per degree Celsius, it is will this be same in percentage per degree Fahrenheit? And in my opinion, it will not be same. It will change because I think in that expression, division comes into the mathematical expression on conversion formula. So it will be it will not similar. But in Celsius and Kelvin, it will be similar. But if you convert either Celsius Kelvin to Fahrenheit, then this quantity will vary. And you know this how you can vary this percentage per degree Celsius into Fahrenheit by multiplying with 9/5, and from percentage per degree Celsius you have to multiply with 5/9. So this is not relevant to our course. I don't think they will ask in Fahrenheit. So we have to just take care of this Kelvin and Celsius. So now coming to this current assignment, that is assignment number 2. So let us solve the problem.
For that, let us place the IV characteristic.
Please turn off your mic. Your mic is. So let us come to assignment 2. So first problem is that 4 non-identical PV modules with non-identical PV cells are connected in the fashion shown below. PV1, PV2, PV3, and PV4 comprise 70 numbers, 50 numbers, 80 numbers, and 40 numbers of cells connected in series, respectively. What is the open circuit voltage in volts of the PV array with the PV cell open circuit voltage of 0.615 volt, generating light current or photo current of 8.6 ampere and 5.6 ampere at 1 kilowatt per meter square for PV1, PV3, and PV2, PV4 modules respectively. So please try all of you, and you can give your answer in chat box. So it is having PV1 having 70 number of cells in series. So this is having 70 numbers of cells, and PV2 having 80 numbers, 50 numbers. And PV3 having 80 numbers, and PV4 having 40 numbers. So here they are asking simpler problem, and they also make it simple by having the same number of cells. By having the equivalent cells, total number of cell in series is equal. So each cell having open circuit voltage of 0.615 volt. So VOC of each cell is having value of 0.615 volt. So here, if we see this, string, then it is having 120 numbers of cells. And since all cells are identical, either it is in PV1 and PV2, so we can directly write 120 number of cells are connected in series. And here, this 80 and 40, so it will also coming as 120 numbers of cell. So you can directly, since number of cells connected in this string and this string, either you can take it as string 1 and this take it as a string 2. Since both strings are having 120 number of cells, then it is very simple to find this open circuit voltage for this entire module, for this PV array. So VOC of array will be VOC of a string 1 equal to VOC of a string 2. So you can multiply with number of cell into the open circuit voltage of each cell. So it will be 120 into 0.615. So it is coming as 73.8 volt. So the correct answer is 73.8 volt, and the range for this problem is given is 73 to 75. Yes, 73 is correct answer. Now coming to the next problem. It is also a simple problem. Consider a photovoltaic string consisting of m PV cell in series, and in such series, photovoltaic strings are connected in parallel, resulting in series parallel configuration. Assume that all the individual PV cells are identical. The open circuit voltage and short circuit current of each PV cell are 2.1 volt and 1.4 ampere respectively. If the short circuit current and open circuit voltage of the overall configuration are 4.2 ampere and 8.4 volt respectively, then the value of M plus N is. So this problem is from the identical PV cells connected in series parallel. So these PV cells are identical. So it makes the problem simpler. So here given that M PV cells in series. M PV cells are in series. M PV cells are in series. So series, what does this series impact? Series connection of photovoltaic cell impact this open circuit voltage. So this M you can write VOC of each string, VOC equivalent and VOC of each cell. So VOC equivalent is given as 8.4 volt, and this VOC of each cell is given as 2.1 volt. So it is coming as 4 PV cells are connected in series. Now the second point, they are given that n such things are connected in parallel. N such series PV strings are in parallel. So N will be ISC equivalent and ISC of each cell will be 4.2 ampere upon 1.4 ampere. So it will be 3 numbers. Therefore, m plus n equal to 4 plus 3 equal to 7. So 7 is the answer. So how many of you give the correct answer? Yes, 7 is the correct answer. All of you are correct. Chandni, Kegar, and Halls. All of you are correct. Now let us see the next problem. Here, a photovoltaic cell configuration that has 3 PV cells in series and 2 such strings are connected parallel. The open circuit voltage and short circuit current of each PV cell are 1 volt and 2 ampere respectively. When the slope of straight line joining x intercept and y intercept of the IV curve of the overall series parallel configuration is ampere volt. So here 3 PV cells are in series connection. Series connection of 3 PV cells, and then strings are of 2 in parallel. You can make the equivalent circuit also, like this will be the equivalent model of this connection. This is the less number of quantities, so we can easily make this equivalent circuit of this series parallel connection. Whoever is getting the answer, you can type in chat box, And if you have any doubt, you can ask me. Now, now we need to know this VOC and open circuit of each cell. So VOC of each cell is given as 1 volt, and ISC of each cell is given as 2 ampere. Now we can find this equivalent VOC of this equivalent cell configuration. VOC of equivalent VOC of cell configuration will be 3 cells are connected in a series connection. So 3 into 1, so it will be give you 3 volt, and short circuit current will be ISC equivalent. So 2 strings are there. So it get multiplied with 2. Short circuit current official is 2 ampere, so it will be 4 ampere. Then the slope of straight line join the x-intercept and y-intercept of the IV curve of the overall series parallel configuration. Then what will the slope of the straight line? Slope of a straight line, we need to find the slope. So slope will be minus of ISC upon VOC. So ISC is 4 ampere and VOC 3 volt, so it will give you minus 1.33 ampere per volt. And the range they have provided for this problem is minus 1.42 minus 1.3. So be careful about this negative slope, because if we make this a straight line, then it is coming with a negative slope. So this is the VOC and this one is the short circuit current, ISC. So this is the slope. And slope will be minus of ISC upon VOC. Any doubt till here? Yes, minus. Be careful about this minus quantity. Otherwise, it will be counted as means whatever you calculated will be wrong. So you have to take care of this minus. Now coming to the next problem. This is little bit lengthy problem, but mathematic. It has lots of mathematics. Not too much. You have to put your mind. So here this PV module is connected to a load. We can see that this is connected to a load as shown below. What is the value of current in amperes flowing in the diode component of the equivalent circuit under maximum power point and standard irradiation of 1000 watt per meter square and 25 degrees Celsius temperature. So you have to find this diode current. And what are the things they have given? This diode expression is given as I naught into exponential of Vd upon Vt minus 1, where this I naught is dark saturation current, whose value is 3.43 into 10 to the power minus 10 ampere. Vd the voltage across the diode, and Vt the voltage equivalent to the temperature, and Vt the thermal voltage, and Vt we get from this expression n into k into t into n cell upon q, where n is the diode identity factor, which is considered 1 here. K is the Boltzmann constant, whose value is 1.38016 into 10 to the power minus 23 meters square kg per second square per Kelvin, and T the operant temperature in Kelvin. N cell is the number of cell connected in series, and Q is the charge of electron, which is 1.6022 into 10 to the power minus 19 coulomb. And they have given this data for this PV module at an irradiance of a standard condition, that is solar irradiance of 1000 watt per meter square and temperature of 25 degrees Celsius. So the number of cells connected in series is 60 numbers, and open circuit voltage is 36.9 volt. Short circuit current is 8.55 ampere. This maximum power voltage is 29.8 volt, and maximum power current is 7.89 ampere. So let us try to solve this problem. So either deadline of this assignment 1 is over, or it is still there. Still you have time.
Sir, I think we have time till 7th of August.
Okay. So one of the problem, I think it is based on this type only in assignment 1. So you can have better understanding by solving this problem. So how we can find this VD voltage across the diode? So let us copy this. So from the data we have given this short circuit current and open circuit voltage of the PV module. Given values are this IMP, maximum power point voltage is given as 7.89 ampere. And this maximum power point voltage is given as 29.8 volt. So since this PV module is operating at the maximum power point, so we can find this voltage across the diode. So how we can find this voltage across the diode? So this IPV will become equal to IMP, that is equal to 7.89 ampere, and therefore we can find this VD. And this VMP across the diode is also known. So You can write one point here. At maximum power point, this IPV equal to IMP, and this voltage across load will be VMP. Therefore, this voltage across the diode will be IMP into series resistance plus VMP. It will be 32.94 volt, the voltage across diode. Now we have to find this diode current. So we know this voltage of the diode. Now we can find the diode current using all the quantities given. So we know the diode current is, expression is this this dark saturation current into VD upon NVT minus 1. So here they have taken this N inside this thermal temperature. So this take it as VT. And thermal temperature expression is given as N into K into temperature into N cell upon Q. So N is the diode ideality factor. And the diode ideality factor, so it is given as 1. And number of cell is given as 60. So be careful. This you have to include the number of cell while calculating the thermal voltage. Whenever you are calculating this diode current, so in this diode current we have thermal voltage. So don't forget to include this number of cell. If this open circuit voltage and short circuit current, this maximum power voltage, maximum power current is given for the entire module in the data sheet. So you have to take care, include this number of cell while calculating this diode current. And this diode current will come into this thermal voltage. So this number of cells will come into thermal voltage. So first we are going to calculate this VT thermal voltage. Let us calculate this VT first. Thermal voltage. So K into T into number of cell upon Q. So K is the Boltzmann constant. K is the Boltzmann constant, and it is given as 1.3806 into 10 to the power minus 23. So temperature should be in Kelvin. So temperature is given as 25 degrees Celsius. So add with 273.15, so it is coming as 298.15 Kelvin. So it will be 298.15 Kelvin, and number of cells are given as 60. So divide it with this Q, charge of electron. So charge of electron is 1.60 to 2 upon into 10 to the power minus 19. So thermal voltage you will get is 1.54 volt. 1.5415 volt. Now you put this VT in the ID expression. So here in the class, one expression more sir has described. So I just want to discuss here. So it is very important and be careful. So in shortcut, if you don't know this Boltzmann constant charge of electron, then no need to worry. So you simply remember this expression. Thermal voltage equal to this 3 upon 11,600. It will give you thermal voltage. So I have one doubt here. So this thermal voltage, whatever I have written here, it will give the value in volt or millivolt. Can anyone tell?
It will be in millivolts, sir.
Okay, Preeti. Yes, correct. So be careful. Means if you are using this expression, then this give the value in millivolt, and you have to put the temperature in Kelvin. So from here you can also find the VT. So VT, just put this temperature 298.15 Kelvin upon 11,600. So this is important. So it will give you number, but here we have not multiplied with number of cell. So in this problem, they have given the number of cell for the PV module. So you have to multiply with number of cell, that is 60 upon 11,600. It is coming as 1.54. I think here what mistake I did. Because here this value is coming as 1.54, but it will give you in volt, millivolt. But here we are getting in voltage. Can anyone tell? I think I am doing some mistake. So anyway, you look up on this. I'm not writing down here. So I think I am doing some mistake in this expression again. So if you know the answer, just tell me. So here we are getting this thermal voltage 1.5415 volt, and this dark saturation current is given in the problem, that is 3.43 into 10 to the power minus 10 ampere, and this VD voltage we have just calculated, that is coming as 32.94 volt. So we will substitute all these values in diode expression, that is I naught into VD upon VT minus 1. So ID will be 3.43 10 to the power minus 10 e to the power 32.94 upon VT is 1.54 minus 1. So it will give you ID equal to 3.4 10 to the power minus 10, and this will be very large quantity, 1911774803 minus 1. This I naught we can neglect, so you can get ID as 0.656 ampere. And the range for this problem they have given, range is given as 0.55 to 0.7. Now let us come to the next question. Which of the following statement is correct? The value of diode current in the equivalent circuit of PV module is maximum under the short circuit condition and minimum under the short circuit condition. The value of diode current in the equivalent circuit of PV module is minimum under the short circuit condition and maximum under the open circuit condition. So all of you please try this question, and I am coming in 1 minute. Yes, VT is voltage equivalent of temperature. Hello. Yes. So here you have to find the diode current when this diode current will be maximum, either in the short circuit condition or open circuit condition. So use this diode expression. So diode expression, we all know that this ID equal to I naught into VD upon diode ideality factor and thermal voltage VT minus 1. So using this expression, you can clearly say that when this diode current will maximum either short circuit or maximum short circuit condition or open circuit condition. So let us see during open circuit. Open circuit condition, we are getting this VD value, some value, we will get some value. So that means this ID will be maximum. ID will be maximum. And during short circuit, voltage across diode will be 0. So if this 0, then this quantity will become 1, and then this diode current will be also 0. So you can say that this value of diode current in the equivalent circuit of PV module is minimum under the short circuit condition and maximum under the open circuit condition. Yes. Anyone are able to give the answer for this problem? Are you able to get the problem? So correct answer is B. Now let us come to the next problem. For this problem is for these non-identical modules that are connected in parallel. So here two non-identical PV modules are connected in parallel as shown in the below figure. If the current in the diode components of the equivalent circuits of PV modules are ID1 is given as 1.9525 ampere and ID2 is given as 31.3628 ampere respectively. The value of DC voltage source is 32 volt. Then the power to the DC voltage source will be, and you have to give the answer in watt. So what are the things we are given? So here this diode current given. So given values are ID1 is given as 1.9525 ampere and this ID2 is given as 31.3628 ampere and this DC voltage given as 32 volt. And all the quantity series parasitic resistances are given in the figure. And this photo current is also given. So we need to find this load current so that we can find the power to the DC voltage source. The power to the DC voltage source is VDC into I load. And I load is unknown. VDC is given as 32 volt. So we need to find this I load. So to find I load, we will use this. We will use KVL here and we can find the I load. So let us first take this first copy this figure and put it here. So this ID1 is known. Therefore, we can say that this ISH1 shunt current for this PV cell 1 and series current for PV cell 1 will be this photo current minus ID1. This photo current is given as 8.551 ampere minus diode current is given as 1.9525 ampere. So therefore, you will get this ISH1 plus I series 1, so 6.5985 ampere. Now, in similar way, for this PV cell 2, shunt current plus series current will be photo current of 2 minus diode current of 2. So photo current is given as 8.55 1 ampere. So both having same photo current, and this diode current is given as 31.3628 ampere. 31.3628 ampere. So it will come as negative to minus 22. So whatever the sign convention we have used in the figure, so we are using that sign convention. So minus 22.8118 ampere. Now we will apply this KVL across this. So we will follow this path. Sorry. We can apply two KVLs here. So we follow this path first. And then, so using applying KVL first here. So going from this DC voltage source, DC load, going through this DC load, DC voltage source. So KVL 1. So VDC, and then we are going opposite of current, so it will be plus 0.3984 I series 1, and we are going in direction of current, so it will be negative minus 3407 I shunt 1. So now we will substitute one value from here, from the expression. From 1, you can say it is 1, it is 2. So from 1, we will get VDC. So VDC is also known. So VDC is 32 volt plus 0.3984 I series 1 minus 3407 I shunt 1 is 6.5985 minus series 1. So from here, you will get series 1 series current through first PV cell as 22449.09 upon 3407.4. So we will get this current as 6.58 ampere. Now to 4.09 upon 3407.4. It will give you 6.58 ampere. Now we apply this KVL in this circuit. So going from this DC side, then we'll follow this PV cell 2. So applying KVL 2. So this will be VDC, and going opposite direction of series current. So it will be 0. Plus 0.2656 IAC2, and going in the direction of shunt current. So it will be 2271 I shunt 2. So here we have using the first expression. Now here we are using the second expression. So it will give you 32 plus 0.2656 I series 2 minus 2271 shunt current. We can write minus of 22.818 minus ISC2. So solving this, you will get series 2 current as minus of 51,837.6 upon 22.71, sorry, 2271.26. So it will give you minus 22.82 ampere. So here we can see that this PV cell one, this PV cell is a sink element. Now this, what is the I load current? This I load current is simply this ISC1 plus ISC2. So this I load current is this AC1 plus AC2. So AC1 coming from this and AC2 current is coming from this PV cell. So you can write I load as I series 1 plus I series 2. I series 1 is 6.5881, 6.588, and minus series 2 current is minus 28.823. So you will get minus 16.234 ampere. So what is the power to the DC voltage source? So VDC into I load. VDC is given as 32 volt. IDC is minus of 16.234 ampere. So it is negative. So it is minus 519.52 watt answer. So the range they have provided is minus 525 to minus 510. So let us come to the next problem. Let us come to the next problem. A PV system is utilized to power a DC motor to produce 3 HP shaft power. The motor efficiency is 82%. Each module has 36 multi-crystalline silicon solar cells arranged in 9x4 matrix. The cell size is 125 mm cross 125 mm, and the cell efficiency is 12.5%. If the global radiation incident normally to the panel is 945 watt per square meter, the number of modules required in the PV array is. So this is simple problem. So how we can find? So let us find the input to the motor. So how you can find the input to the motor? Input power required for the motor. So if input power to the motor will be this 3 HP shaft power, but the motor efficiency is 82% only. So we have to provide more power than this 3 HP. So you can also write input power to this HP to this DC motor equal to the output power of PV system. Output power of PV system. So output power of PV system is this rated, this rated value of DC motor upon efficiency of this motor. So rated value is 3 HP. So 1 HP equal to 745.7 watt. So this is very important. So 3 into 745 5.7 watt, and efficiency of motor is 2%. So output of power of PV system should be 2728.17 watt. Now, how we can find this output power of PV system? So using this efficiency, we can also find this output power of PV system. Sorry. So output power of PV system. So P output upon P in. So efficiency of cell is given as 12.5. 12.5. So each cell efficiency they have given. And the number of cells are 36. So it's better to write in this way. So P naught equal to efficiency of each cell into this number of silicon cells, the number of cells into area of each cell, and into this insulation. Insulation we denote by L. And then we are having this number of modules that we need to find. So we have calculated output power 2272.17 watt, and efficiency of each cell is 0.125. Number of cell is 36. Area of cell is 125 into 125 millimeter into meter square, 10 to the power minus 6 meter square. And then this 945 watt per meter square is the insulation, and then we can find the number of PV modules in the PV area. So solving this will give you 41.058. So correct answer for this problem is C, 41. How many of you able to solve this problem? I think many of you able to solve this problem. I don't know how many of you. Please, all of you try. So let us come to the next problem. So this problem is from the theoretical type problem. Here, let us now look at a method where we will able to see the IV characteristics on an oscilloscope so far that let us draw the circuit diagram as shown in the figure. This is the PV module with the protection diodes, both series and parallel protection. Let us terminate the PV module now across the terminals. Allow us to draw now not a load but our voltage source. Just like we did in simulation exercise, then incorporate a series resistant here called R-sense. And here the VT signal acts like a sweep for the external triggering of the oscilloscope. Therefore, the amplitude should be related to the amplitude of PV module voltage. What will the voltage source characteristics be incorporated as load in the circuit diagram? So this problem is from directly lecture 22 This problem is from directly from lecture 22 practicals. Measuring IV characteristics. So if you able to solve this, if you able to if you have gone through this lecture, that is practicals measuring IV characteristics, and there professor has explained this characteristics of this voltage source. So this voltage source should be unidirectional voltage and capable of sinking current. So you refer the slide time 6.12 for this problem. Correct answer will be C. It should be unidirectional voltage and capable of sinking current. If this voltage source goes negative, there will be large sinking current, and there will large surge current for the circuit, and something will have to blown up. So this should be have unidirectional voltage. Yes, you can reply the answer for this problem. Now let us come to the next problem. It is similar. It is same from the same lecture. That is measuring the IV characteristics. How we can measure the IV characteristics of a PV cell. So irrespective of directly putting a voltage source, we are using the AC supply. And first, this AC supply is connected to this auto transformer, and this auto transformer lowering down this voltage to 18 volt. And then we are having this rectifier, and this rectifier will provide this positive side voltage only. And then here we have BJT. So with this circuit, we can get the IV characteristics with the help of this R sense. So here we are not using differential probe for the measurement. So in this problem, they are asking about at what connection point you have ground probe, measurement probe, rigging probe in the correct way for the IV characteristic measurement in the figure. So D, if you see, refer to this lecture number 22, practicals measuring IV characteristics. So D is the common probe. D point is the common probe. Common probe, that means it is ground probe. So D is the ground probe, and we are measuring the voltage across this R sense. So this one will be the measurement probe. E point will be the measurement probe. So here you will get this. Here you will get the negative voltage. So you have to invert this V sense. So this one you have to V sense you have to invert. So this voltage you need to invert so that you can get the correct voltage output. Because here this positive terminal is grounded and this negative terminal we are measured. So this you need to invert. So this is measurement probe, and this one is the B point is the TV probe. So correct answer for this problem is D, E, and B. Now let us see the next problem. And this problem is on the PV emulator. Because I have shared this answer. It should be in directional voltage and capable of sinking current. So this voltage source should have unidirectional and this capable of sinking current. In spite of putting this voltage source, we can find the better solution by using this circuit, electronic circuit, with the help of auto transformer and this rectifier circuit and this triggered BJT. Now let us come to the next problem. Here, this problem is based on the PV emulator. So here this PV source, the figure shows the block diagram of the PV emulator based on the currently controlled DC-DC converter. I and V are terminal current flowing through the load and the terminal voltage across the load. The reference current for the currently controlled DC-DC converter is generated using the lookup table of this IV characteristics. So we are using this lookup table for generating the reference current based on the measurement of voltage. And suppose this PV emulator is working for a particular load R and suddenly the load to the PV emulator increased, then what will happen to the reference current generated by an error seen by the PI controller? So I have one question here. So if load is increasing, then this here they are saying that load to the PV emulator is increased. So load is increased. So that means R0 will increase or decrease. Can anyone tell? Can anyone tell? R0 will increase or decrease? If we are increasing the load, then the resistance should be increased or decreased. You see, you are typing the correct answer, but I am asking a different question. This R0 will increase or decrease? Anyone? Preeti,
Increase.
Chand?
Increase.
No, this R0 will decrease. This R0 will increase. R0 will decrease. If R0 will decrease, then this I1 upon R0 will increase. So here, if you see this curve and refer to this IV characteristics, then this one is this blue line denotes this previous case, and on increasing the load, then increasing the load means you are decreasing the resistance. That means you are shifting down this value, and that means that this IT current will get reduced this reference current. So based on this, if you see this according to this load line, and this IT will get reduced. So IT will get reduced, and error will be whatever the previous value we have. This error will be in negative. So correct answer for this problem is C. Now coming to the next problem. So in this problem, a PV panel is emulated by a voltage source in series with resistance. The specification of two PV panels are as follows. PV panel 1 having open circuit voltage 44.83 volt and short circuit current of 8 point short circuit current of 8.9 ampere. And for PV panel 2, open circuit voltage for 45.1 volt and short circuit current is 9.25 ampere. Assuming there is no protection diode, the open circuit voltage when the panel connected in parallel will be. Okay, please solve this problem. So here you see the case. So let us assume this as V1 and this as V2. So RS1 and RS2. This is open circuit voltage, that is 44.83 volt. And this is open circuit voltage 2. This is 45.1 volt. So, and short circuit current VOC1 is 44.83 volt and ISC1 is 8.9 ampere. So this will give you RS1. So VOC1 upon ISC1, that will 44.83 upon 8.9. So RS1 will be 5.0371 ohm. And for the second cell, VOC2 is 45.1 volt, and ISC2 is 9.25 ampere. So RS2 will be 4.8757 volt ohm. Therefore, circulating current in the circuit will be, so let us see the circulating current starting from this and then going towards this. So apply KVL. Circulating current in the circuit will be VOC 1 minus I RS1. Let us take it as I. Circulating current minus I RS2 minus VOC2 equal to 0. So from here you will get minus 0.02723 ampere. So you can find VOC either way. Either you put VOC2 minus IRS2. So you will get 45.1 minus 0.0273 into 4.857. So you will get 44.96 volt. So answer belongs to the range from 44.9 to 44.99 volt. Now coming to the next problem. Here 6 identical PV modules with open circuit voltage of 37 volt and short circuit current of open circuit voltage is of 37 volt and short circuit current of 10 ampere. So each module. So if module 3 is fully shaded. So if module 3 is fully shaded, it is fully shaded. The short circuit current from A to B of the system is, you have to find the short circuit current from A to B. So short circuit current of module 1 and 2. So this short circuit module 1 and 2 will be, so module 1 and module 2 will be 10 ampere. And short circuit of module 3 and module 4 will be also 10 ampere and short circuit. So all are identical. So you will get short circuit current of module 3 and 4. This shaded one also 10 ampere. Module 3 and short circuit current of module 5 and module 6 10 ampere. Here if you consider each series combination a single module, this combination of 1 and 2 and 5, 6 having short circuit current of 10 ampere and open circuit voltage of, if you find this open circuit voltage, then you will get, like if you don't consider this fully shaded, so one this module and this module, then you will get this VOC equivalent will be 74 volt and this VOC equivalent will be 74 volt. While this shaded portion, you will get VOC equivalent will 37 volt since this module 3 is fully shaded. And during short circuit from A to B, total current will be the sum of all this. That means short circuit current from A to B will be sum of all 10 plus 10 equal to 30 ampere. 30 ampere will be the answer. Now coming to the next problem. Here, 4 identical PV modules are connected to configuration, namely configuration 1 and configuration 2. In configuration 1, in configuration 1, VOC equivalent will be all PV cells connected in series. So 4 into VSC, and in configuration 2, all PV cells are connected in parallel. That means VOC equivalent will be VOC of each cell. So assuming the same solar insulation and following on each cell, the terminal open circuit voltage of configuration 1 will be what? So configuration 1, you can write it as 1 and you can write it as 2. So VOC equivalent 1 will be 4 times of VOC equivalent 2. So correct answer is 4 times. So range is given as 3.9 to 4.1. And for the previous question, range is given as 29.9 to 30.1. Now coming to this next problem. A PV panel consists of 10 PV cells. Each PV cell has an identical protection diode across it and has open circuit voltage of 2 volt. So open circuit voltage 2 volt. The PV panel is connected directly to a battery. Accidentally, the user interchanges the battery terminals while connecting to the PV panel. Under this condition, the voltage across the PV panels. So if you incidentally connect the voltage, the battery terminals interchanged. That means you are forward biasing the protection diode. All the diodes will in the P panel get short circuited. So since it is ideal protection diode, ideal protection diode have cut-in voltage of 0 volt. So all are forward biased. So this all the diodes in the PV panel will get short circuited. So under this condition, the voltage across the panel will be 0 volt. So 0 volt is the correct answer. Coming to the next problem. Two non-identical PV panels are connected in series. They have open circuit voltage of 10 volt and 40 volt. If both panels are connected in adding polarity, then the terminal open circuit voltage of series combination will be. So this is very simple. VOC terminal will be one having 10 and one having 40 volt. So 10 plus 40, that means it will be 50 volt. So 50 volt is the answer. And range is given for this problem is 49.9 to 50.1. And for the previous problem, the range is given as minus 0.1 to 0.1. Now let us see the next question. In this question, two solar cells, namely cell 1 and cell 2, are connected series to deliver the load power. The characteristics of two cells are shown in the figure below. Due to some atmospheric condition, the cell combination is operating region 1 of the IV characteristics. Then which of the following statement is true? So the cell combination is operating in this region, region 1. So in this region, we can say that this cell 1 is generating while this cell 2 is sinking power. So here is this, the correct answer is A, because the current demanded by the load will be greater than the ISC2 for any operating point in region 1. And in this cell characteristic, the cell number 2 will be sinking power and the cell number 1 will be sourcing power. Now coming to the next problem. If the photovoltaic panel has 4 identical modules connected in series and 4 such strings are connected in parallel, each module has an open circuit voltage of 20 volt and short current of 4 ampere. What should be the open circuit voltage and short circuit current of total system? So it is very simple. 4 cells in series. That means VOC equivalent will be 4 into 20. It will give you 80 volt, and 4 such strings are in parallel. 4 such strings are in parallel. That means short circuit equivalent current will be 4 into 4 ampere. That will give you 16 ampere. So correct answer will be B. So this is the last problem. That's all. I hope you are able to get all the question. Please share question 13. Please share question 10, 11. 13 number. Yes. This is very simple. You just read carefully and try to solve. I think you are able to get it. And question 11. This one is also simple. To try yourself and see this recordings or refer this slide. You will able to get this question. So here in this problem, we first find this circulating current. Means here this refers to this like sourcing panel, sourcing PV panel and sinking PV panel. So that is similar to this PV panels. Means emulating the PV panels. This ideal, this practical PV panels. Any other doubt? Thank you all for attending this session. If you have any other doubt, you can ask me. Thank you, Vasaveswar. You are able to get all the recordings.
Yes, sir.
Yes, in Swayam portal. In Swayam portal, you can.
Yes, sir. All recordings
go-
are available easily.
Yeah, so here you can get all the recordings, and all of you please join this question answer, that is discussion forum. Here you can ask questions. Means here all the members are present. All the members who are related to this course, all members are present. So if you ask here this question, we will give the answer in a better way. This is also very important discussion forum. Okay. All the best and good night.
Thank you, sir. Good night.
Okay, bye.
So